Most people have spent their entire lives thinking about the solar system in one direction, sideways. The planets orbit in a flat disk, the sun sits in the middle, and every image we have ever seen of our solar neighborhood shows everything arranged on a single horizontal plane. But almost nobody ever asks what is directly above and below the sun. And the answer, when you actually go looking, is one of the most extraordinary stories in all of modern astrophysics, involving invisible magnetic chaos, a protective bubble blown by ancient supernovae, a chimney that vents into the galaxy's outer halo, and scientific discoveries so fresh that the first photographs of what lies above our star were only taken in 2025. Let us start with the sun itself, because before you can understand what is above and below it, you need to understand what the sun's own north and south poles actually are, and why, until very recently, no human being had ever seen them. Every telescope, every spacecraft, every image of the sun ever captured before 2025 was taken from within the ecliptic plane. The ecliptic plane is the flat disk in which Earth and all the other planets orbit the sun. Because humanity has always observed the sun from within this plane, from a perspective that is essentially sideways on, the sun's equatorial regions have been extensively mapped, studied, and imaged in extraordinary detail. But the polar regions, the areas directly above the North Pole and directly below the South Pole, were essentially blind spots. They sat at an angle that no spacecraft had ever climbed high enough to observe directly. Scientists knew they existed, they suspected they were important, but they had never actually seen them. That changed in March 2025. European Space Agency's Solar Orbiter spacecraft, executed a Venus flyby in February 2025 that tilted its orbit out of the ecliptic plane for the first time. On March 16, 2025, with Solar Orbiter now angled 17 degrees below the solar equator, human instruments got their first direct look at the sun's south pole. The images and data that came back from that flyby were described by ESA project scientist Daniel Miller as just the first step of Solar Orbiter's stairway to heaven. The beginning of a years-long campaign that will see the spacecraft climb to progressively steeper viewing angles, eventually giving humanity an almost directly overhead view of the top and bottom of our star. What did those first images reveal? Chaos. One of the earliest scientific findings from Solar Orbiter's polar observations was that the magnetic field at the sun's south pole is, in the words of ESA's announcement, a mess. Instruments aboard the spacecraft detected the simultaneous presence of magnetic fields of opposite polarity at the south pole, a tangled, contradictory, chaotic magnetic configuration that is completely different from the relatively orderly magnetic structure seen at the sun's equatorial and mid-latitude regions. This kind of magnetic chaos is expected during the peak of a solar cycle, when the sun's global magnetic field is in the process of flipping its polarity, the north magnetic pole becoming south and the south becoming north, an event that happens roughly every 11 years, in which the sun's cycle 25 was approaching its maximum during exactly this period. But the degree of disorder was surprising even to specialists. Scientists described never knowing exactly what to expect from the first polar observations, calling the sun's poles literally terra incognita, unknown territory. The data continues to be analyzed, with the complete dataset from Solar Orbiter's first full pole-to-pole flight expected to be fully processed and published through late 2025 and into 2026. There's also a finding about speed. Analysis published in November 2025 in the Astrophysical Journal Letters revealed that the sun's magnetic field lines at the South Pole are drifting toward the pole at approximately 10 to 20 meters per second, about the speed of a brisk bicycle ride for a star with a radius of nearly 700,000 kilometers. What makes this surprising is that this drift rate is similar to what is observed at lower latitudes, suggesting that the mechanism carrying the magnetic field toward the poles operates with consistent physics across the sun's surface, a finding that has implications for how scientists model the solar cycle and predict the sun's activity behavior over decades. The solar wind connection is the reason this matters beyond pure curiosity, directly above. And below the sun, the poles are the birthplace of what is called the fast solar wind, a stream of charged particles that flows outward from the sun at speeds of up to 800 kilometers per second. This fast polar wind is fundamentally different from the slower, more variable solar wind that emanates from equatorial regions. Understanding exactly where and how this fast polar wind originates has been a central unsolved problem in solar physics for decades. Previous observations of these polar outflows were limited to the grazing views available from the ecliptic plane, which provided only a sideways look at the process. Solar Orbiter's direct polar perspective, as SPICE team leader Frédéric Aucher of the University of Paris-Saclay put it, will be a revolution in solar physics. The full understanding of why the poles generate the fast solar wind is still being built from Solar Orbiter's new data. But the picture emerging is one of concentrated openness. Magnetic field regions at the poles, areas where the sun's magnetic field lines extend straight out into space rather than looping back to the surface, through which plasma is accelerated to extremely high velocities. These open field regions funnel material away from the sun and into the heliosphere at speeds that the slower, looping equatorial field regions cannot generate. Now let us zoom out, because above and below the sun's poles is not just the sun's own magnetic domain. Moving outward from the poles, the sun's influence extends into what is called the heliosphere, a vast bubble of solar wind and magnetic field that the sun inflates around itself, expanding outward in all directions until it meets the interstellar medium. The heliosphere is the boundary of the sun's direct influence. Inside it, the solar wind dominates. Outside it, the interstellar medium takes over. The shape of the heliosphere above and below the sun is significantly different from its shape in the directions where the planets orbit. Along the ecliptic plane, the heliosphere is compressed in the direction the solar system is moving through space, like the bow of a ship pushing through water, and elongated in the trailing direction. But above and below in the polar directions, the heliosphere expands more freely because the resistance from interstellar material is lower there. The heliosphere, in cross-section through the poles, is effectively funneled upward and downward, wider in the polar directions, extending hundreds of astronomical units above and below the solar plane before the interstellar medium begins to push back. In 2004 and 2007, the Voyager 1 and Voyager 2 spacecraft crossed what is called the termination shock, the boundary where the solar wind slows down from supersonic to interstellar material. Voyager 1 crossed this boundary at approximately 94 astronomical units from the sun. Voyager 2 crossed it at 84 astronomical units. Both crossings happened near the ecliptic plane, not directly above or below. Scientists believe the termination shock in the polar directions occurs at somewhat different distances, though the exact polar geometry of the heliosphere's boundary remains one of the open questions that NASA's IMAP mission, the Interstellar Mapping and Acceleration probe, launched on September 24, 2025, is specifically designed to answer from its position at the Sun-Earth L1 Lagrange point. Beyond the heliosphere, what lies above and below the sun is something that was created long before the solar system existed, and will exist long after it is gone. It is called the local bubble, and it is one of the most remarkable structures in our galactic neighborhood. The local bubble is a vast, roughly spherical cavity in the interstellar medium, the gas and dust that fills the space between stars in the Milky Way. It spans at least 300 light years across, though its boundaries are irregular and extend much further in some directions than others. Inside this cavity, the density of interstellar gas is about 1/10 of the already thin galactic average. The local bubble is, in essence, an enormous bubble of near vacuum that the sun and its neighboring stars are currently traveling through. How did it form? The leading explanation is supernovae. Between 15 and 20 million years ago, a sequence of massive stars in the Scorpius-Centaurus stellar association exploded one after another. Each supernova blasted a shockwave outward through the surrounding interstellar medium, sweeping gas and dust ahead of it like a giant invisible plow. The combined effect of these successive explosions hollowed out a vast region of space, blowing a cavity in the galaxy's interstellar medium that became the local bubble. The sun did not enter this cavity until approximately 5 to 10 million years ago. Before that, it was traveling through denser interstellar material. For the past several million years, the sun has been sailing through this enormous cleared region, largely empty by interstellar standards, surrounded by the hot, sparse gas that fills the bubble's interior. The temperature inside the local bubble is approximately 1 million degrees Kelvin. That sounds extraordinary, but it is hot in the way that the corona of the sun is hot. Extremely energetic particles spread so thinly that the total heat energy involved is actually very small. The bubble is not a furnace. It is a near vacuum of hot, sparse plasma, emitting low-energy X-rays that were first detected by X-ray satellite missions in the 1970s and have been studied in detail since. Now, here is the detail that directly answers the question of what lies above and below the sun. The local bubble is not a sphere. 3D mapping of the bubble's structure using dust measurements and stellar observations reveals that it is narrower in the plane of the Milky Way galaxy, where denser interstellar material presses in from surrounding regions, and significantly wider above and below the galactic plane, where the gas density drops off rapidly. In cross-section, the local bubble has been described as egg-shaped or hourglass-shaped, widening toward the galactic poles. And in the directions directly above and below the galactic plane, the bubble appears to be open-ended, not a closed cavity, but a structure that vents upward and downward into what astronomers call the galactic halo. This open-ended structure has been given a more accurate name in recent astrophysical literature. It is described not as the local bubble, but as the local chimney, a cavity that does not close above and below, but instead funnels into the vast hot atmosphere that surrounds the disk of the Milky Way. Research published in 2024 using high-resolution three-dimensional dust mapping confirmed this chimney geometry, finding that the bubble's surface falls off rapidly above the galactic plane in a pattern consistent with an outflow that is vented into the galactic halo. What is the galactic halo, this region that the local chimney opens into above and below the sun? It is the enormous, diffuse, mostly hot and ionized atmosphere that surrounds the flat disk of the Milky Way like a ghostly envelope. The galactic halo extends for tens of thousands of light years above and below the galactic plane. It contains ancient stars, globular clusters, streams of stars torn from dwarf galaxies over billions of years, and vast quantities of hot ionized gas. It is the region through which high-energy cosmic rays travel on their way into the galactic disk. It is where material blown out of the disk by supernovae and stellar winds eventually ends up cooling, and eventually falling back as what astronomers call the galactic fountain, a slow cycling of gas between the disk and the halo that operates on timescales of tens of millions of years. In December 2025, NASA's Fermi Gamma Ray Space Telescope revealed a dramatic illustration of exactly this process. A young stellar cluster called Westerlund 1, located slightly below the galactic plane, was found to be blowing an enormous bubble of gamma rays extending over 650 light years below the galactic disk, a nascent chimney driven by the combined winds and explosions of the cluster's massive stars, venting hot, energetic material out of the disk and into the halo in real time. Westerlund 1 is doing today what the supernovae that created our local bubble did 15 to 20 million years ago, evacuating a cavity in the interstellar medium that will eventually open into the galactic halo and leave its own local chimney structure in the fabric of the galaxy. So, what is directly above and below the sun? Starting at the closest scale and expanding outward, the answer is this. Directly above the sun's north pole and below its south pole lies a magnetic frontier, a zone of tangled, reversing, barely mapped magnetic chaos that generates the fast solar wind and holds the key to understanding the sun's 11-year cycle, first observed directly by Solar Orbiter in 2025, and still being actively decoded. Moving further out, those poles feed into the heliosphere's most open corridors, the polar regions where the sun's bubble of influence expands most freely into surrounding space. Beyond the heliosphere, in all directions above and below the solar system, lies the interior of the local bubble, a vast, hot, near-empty cavity in the galaxy's interstellar medium, blown out by supernovae millions of years ago, through which the sun has been sailing for the last several million years. And above and below that cavity, the local bubble opens into the galactic halo, the enormous, ancient, diffuse atmosphere of the Milky Way, stretching for tens of thousands of light years in every direction, containing the oldest stars in the galaxy and the slowly cycling gas of a billion-year-old stellar ecosystem. From the sun's poles to the edge of the Milky Way's atmosphere, that is what lies above and below us. And most of it, until very recently, had never been seen by any instrument that humanity had ever built.